Okay, so here's what we were talking about last time. We're talking about the diagonalizable case. So specifically, we're looking at a homogeneous, constant coefficient, first order system, linear. And what happens if this matrix here is diagonalizable? And so the big idea was, keep in mind, a diagonalizable matrix is a matrix which, if you just do a change of basis, becomes diagonal. In other words, it's a matrix which is dramatically simplified by way of a change of basis. So as you might expect, one would think that a change of basis might then, in addition to simplifying the matrix, also simplify the system. And that's exactly what happens. You take the matrix, replace it with the, what you might call the diagonalization of it. In other words, PDP inverse. And then a little bit of algebraic sleight of hand. Just put the P over on the other side as P inverse. And make a substitution here. P inverse Y, just call that Z. Right? And lo and behold, we have now a much easier system. So we talked about the details last time. This is a much easier system because it is decoupled. None of these equations involve the functions of any of the other equations. This is not a, nasty n by n system. This is just n separate count two differential equations that we already know the answer to, right? So everything falls into place at that point. Now, there are a bunch of details to carry through. These are the solutions to those natural growth equations, which makes this general solution, which I can rewrite as linear combinations like this, thus allowing me to infer these functions here as being a fundamental set. Now, of course, those are fundamental set for the Z system. That's not what we were originally interested in. We're interested in the Y system. And multiplying through by the P matrix, we end up with these solutions. And, of course, this was an entirely general calculation that we just did here. This applies to any diagonalizable matrix. And so not only do we have the result for a question, we have a theorem. And here is that theorem. This is about where we left off last time. So, big punchline, when the matrix is diagonalizable, whatever the eigenvalues are, go there. Whatever the eigenvectors are, go there. And the solutions to that system are these. So very compact and succinct little result, in fact. So very nice that this works out this way. Okay, so that closes a we had this dangling thought when we were talking about, in section 6.1 we were talking about how to use linear algebra to solve systems, and I pulled a couple of rabbits out of a hat and said, well, by the way, here's a couple of solutions, and then look at all the linear algebra we can do. Look how we can totally crush the problem at this point with linear algebra. But where did those two solutions come from? Well, they came from exactly this theorem. We were looking at that system. Those are the known eigenvalues that we found long ago. Those are the corresponding eigenvectors that we found long ago. And notice, eigenvectors go there. Eigenvalues go there. And there's our fundamental set of solutions, just following the above theorem. So that's where they came from. Everybody happy with that? Does anybody have any questions before we go on? Okay. All right, so one more example. This next example, though, addresses the complex case. So remember that sometimes, unfortunately, sometimes you'll end up with complex eigenvalues and complex eigenvectors. So what do you do in that case? Well, the exact same thing, really. Your eigenvalues go there. Your eigenvectors go there. and you're kind of done in a certain sense. The only thing is, obviously, somebody asked us a real question. They probably want a real answer. This is complex valued answer. So this is really, it's not ideal. This is kind of unfortunate. So we don't stop here. By the way, in this course, it's my intention, unless I specifically state otherwise, it's my intention that I always want real valued solutions, right? So this would not be an okay answer if this were a test question. So the point is we have to figure out how to turn this into real valued solutions, and we're going to do the same thing that we did back in Chapter 4, namely, we're going to take this conjugate pair. Notice that you have a conjugate pair of solutions there. That's always going to happen. The eigenvalues will always be conjugate pair. These solutions will also always be conjugate pair. So that conjugate pair of solutions, by a linearity argument, just like in Chapter 4, we can take the real part and the imaginary part. Those are a corresponding real pair of solutions that we sort of replace this with. So punchline, we got to multiply this out and figure out, for one of these, and let's take this one arbitrarily. What's the real part of that? What's the imaginary part of that? It's just complex arithmetic. Algebra. Okay, so first of all, the e to the ix, the e to the 1x, you can pull that out. The e to the ix that's left over, you can write with Euler's formula. Right? Now, notice we've sort of gotten rid of this the awkwardness of this being in sort of polar form. This is in rectangular form. I hate it when that happens, right? I mean, you can't. What do you do with that? We don't have any rules for how to multiply like that. So now we've got rectangular times rectangular, and you just multiply it out. So let's look at real terms. Obviously, the e to the x comes down for all of them. Ditto. Okay. Now let's look at real terms. That's real. That's real. That's real. That gives us these terms, right? Imaginary times imaginary. That. Don't forget I times I is -1. Gives you those terms. Right, so the real terms in the product come from real times real and imaginary times imaginary. Okay. Alrighty, then the other way to get imaginary terms in the product. Real times imaginary gives you those terms. Right? Imaginary times real gives you these terms. So that's the imaginary part of the product. Okay, so grand total then, notice we have real plus I times imaginary, and we can then replace these two solutions with these two solutions. Just like we did back in Chapter 4. Everybody see the strategy there? Bunch of details of complex algebra. Okay. All right, so, finishing the thought. Okay, so this first function in our original fundamental set stays along for the ride. Again, we sort of replace these two with these two like that. Okay. All right. So now on to the non-diagonalizable case. So remember, all of this discussion here, everything and how it worked out so wonderfully and the whole change of basis business was all on the assumption that the matrix was diagonalizable. And you can see now why we care, right? Diagonalizable was just indispensably valuable because that's what allowed us to turn it into a diagonal system. And that was indispensably valuable because that's what allowed us to decouple the original system. And the fact that it's decoupled is the only reason we could solve it at all in the first place. Right? So diagonalizability was huge. So what do we do now in this non-diagonalizable case? And we're going to try to do the same thing. We're going to say, well, look, if it's non-diagonalizable, it's not conjugate to a diagonal matrix, but at least it's conjugate to an almost diagonal matrix, right? It's conjugate to this Jordan form matrix, whatever that is. And does that help us? And it turns out that it does. It's just not as nicely. So ultimately the answer here is going to be less convenient than the beautiful answer that we just got finished with in the diagonalizable case. But same deal, you take the P, move it over to the other side, right? You substitute P inverse Y as Z, just like we did in the diagonalizable case. In other words, we do a change of basis, just like we did in the previous case. And we get this. This is not diagonal, so this is not decoupled. At least it's not fully decoupled. And so, sad, right? But it turns out that this is actually a lot of progress, and you can still solve the system. So here's an example to see how this breaks down. Let's apply that idea to this system, y prime equals ay, where this is our matrix. And by the way, this matrix A, I'm going to take it as a given that we know how to do this breakdown. And this is, you'll notice this is a change of basis. We've got P, J, P inverse. So here we have A written as a conjugation. Notice that this J matrix written here is a Jordan form matrix. So A is conjugate to that Jordan form, and because of the uniqueness of Jordan forms, not only is this a Jordan form for the matrix, but we know that this is the unique Jordan form for the matrix, up to rearrangements of blocks, which we don't care about. Okay, so we've got a Jordan form, and that Jordan form tells us that when we do all this business up here, it get down to the reduced, the Jordanized system, that's going to be this. Okay, and not decoupled, right? There's Z2s in my Z1 equation, so I can't just solve for Z1. There's a Z3 in my Z2 equation, so I can't just solve for Z2. However, I can totally solve for Z3. Right? There's nothing but Z3s in the Z3 equation, so you can solve for Z3. And then, hey, here's the deal. Once you've solved for Z3, now you know everything in the Z2 equation other than Z2. So you can solve for Z2. It's just that now this equation for Z2 is just a non-homogeneous first order equation. So you can solve for Z2 in the Z2 equation. And once you know Z2, you can see the pattern here. Right? Once you know Z2, well, now, even though the Z1 equation is not natural growth, it's still, I know everything in the Z1 equation except for Z1. So now I have a non-homogeneous equation to solve for Z1. So I can solve this one as well. And that's the process. So this is called back solving, which is, I think, unsurprising because you sort of work backwards, right? You start from the end, work your way back. And it's a little tedious, but it'll get it done. Okay, so let's, I'm going to do this kind of quickly because there's a lot of details in here. That third equation, there it is. It's a natural growth equation, so we can immediately write down the solutions. By the way, normally for this, what I've written C3 there, normally I would call it like A or something. I'm going to call it C3 for two reasons. First of all, it's the constant that corresponds to the coefficient Z3. So that seems like a natural choice, right? But also for another reason that will make itself clear in a couple of minutes. So for the moment, let's just run with it. Anyway, that point is that's just some constant. Okay, so there's my Z3. My Z3, you will recall, goes there in the second equation. So, in this second equation, notice that it's non-homogeneous. And how do we solve non-homogeneous equations? Well, we refer back to section 4.3, right? You got to find a particular solution. You got to find the homogeneous solutions, and then you add them. It's just an old chapter 4 thing. So, some reminders on that. The homogeneous solutions, looking just at that part, there's the homogeneous solutions in yellow. Right? Notice my choice C2 there. Again, it'll reveal later why I'm making that choice. But those are the homogeneous solutions. To find a particular solution, you've got to play that game. You've got to, form your guess and then, plug and solve for your undetermined coefficients. It's all 4.3. Be careful on this one. Not coincidentally, the naive guess fails. Right? Remember, we have this whole rigmarole for how you deal with forming the right guess. First, you make a naive guess, looking at the form of your right hand side, and based on that form of the right hand side, you would form your naive guess might be that. Right? Looking only at the right hand side. But don't forget, you've also got to look over here at your characteristic polynomial. Your characteristic polynomial is lambda minus 4. Your magic number here, a plus bi, is 4. And the question, the unfortunate coincidence we have to be on the lookout for is this magic number a root of that characteristic polynomial? And sadly it is. Well, everybody happy? Got an unfortunate coincidence. So your guess can't just be the naive guess. You've got to put in this extra factor of x in here. Everybody good? Yeah, a bunch of algebra ensues. You take your guess and you plug that into the differential equation, and out comes this, and chug, 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 and here's your A. A ends up being C3. Okay. All right, so C2, let's see here, so this C3, this A is C3, thus making that turn into this. Right, our homogeneous solution was that. And so there's your Z2. So it's kind of a pain, isn't it? Everybody on board, though? You ever see the process? There's details. Okay. All right, I'm going to let you all do the last one here on your own. Bad news, we have another unfortunate coincidence. You got to look at your right-hand side, figure out what your magic number is. It's 4. Right? Look at your characteristic polynomial. Again, lambda minus 4. There's our unfortunate coincidence. Gives us an extra factor of x. This is our guess. The equation turns into that. Fair amount of calculus ensues, and you can solve for your B and your C. That's your B and your C, which makes your particular solution turn into that. The homogeneous solution, again, is that. And there's your solution. So I just glossed over a lot of details, right? Make sure you can fill in those blanks. Make sure you can do those details. That's the process. And we're still not done. So don't forget what we were doing here. All this Z business, we were looking at these 3 equations. These are the Z equations that come out of the Jacobian matrix, which corresponds to the, well, not decoupled, but, reduced coupled, Z equation. Right? So now we know the Z. We know Z1, Z2, and Z3 after the back solving, but Z is not what we wanted. What we wanted was Y. Y is equal to P times Z. So I've got to take all of this business, that I just solved for, Z1, Z2, and Z3, and I've got to multiply by that P matrix. So by the way, this is one of these situations where it's really important to be able to identify what that P matrix is. Now, for example, I have, on some situations, given students arithmetic like this, but I've gone ahead and inverted this matrix. I mean, the way it's written here, it kind of seems to be implying that the one on the left is the P, and the one on the right is the P inverse, because it's written as something inverse. It really looks like that's probably P inverse, so it's suggestive of that, right? But if it were given where, here's a matrix of numbers, there's your Jacobian, and then here's just another matrix of numbers, and it's not clear which one of these is the P and which one of these is the P inverse. You've got to be able to think it through, right? Realize how the decoupling, the attempted, mostly failed decoupling, how did that work? Where's the P? Which one in the arithmetic is the one that is the one, right? And thus, which one you're going to be multiplying by, right? I mean, in order to get your Y's, you've got to multiply your Z's times the correct P. Okay. By the way, keep in mind, my goal in this course is for y'all not just to be able to, plug and chug into formulas, but I want to make sure that y'all are understanding ideas and that you could hit the curveball, as it were. So, the way I've written this arithmetic here was designed to be, the first time through this process, I want to make it as transparent as possible, right? But you can see how I could obscure the situation a little bit by, as I was suggesting, actually inverting this matrix, thus removing the hint as to which one is P and which one is P inverse. At some point in the past, and I don't remember when this was, I was feeling, a little devilish. And I did something along the following lines. This arithmetic's going to be all wrong, but so, here, let me scratch out like this. So there was some other A matrix, and I basically gave it as something like this. And that was mean. Right? Now, students can still see what the, mostly diagonalized system was. They can go through to the back solving. They can find the Z's. But then the students that aren't paying attention would look at how this is written and say, oh, okay, well, this looks like my P matrix, and that looks like my P inverse matrix, but it's not. Right? So you have to think through, well, wait a minute, which one, go back up to the decoupling process, the change of basis process, and you've got to realize that, look, the one on the left, the one that's being multiplied by J on J's left, that's the one that's P. And so to figure out the P matrix, students would have to invert this matrix. Right? Now, here's the good news. In a case like that, I would just make a decision in advance as to how many points am I going to count off for students who weren't paying attention and who used the wrong matrix as their P. Right? And so, certain, students that weren't heads up would just lose a prefixed amount. And the point is you can work out and see, what the resulting answer would have been, subject to that error. And it's a control. It's not like it makes the problem just go absolutely, unrecoverable, right? Nevertheless, this is something you kind of have to watch out for because it is not always clear which one's which. So heads up. Yes?
Can you explain really quickly how you got from your solutions to the equations to the matrix?
Say it one more time, I'm sorry.
How you got from your solutions to Z to P?
How I got from solutions...
From your solutions like Z1, Z2, Z3.
Oh, okay, yeah. Okay, so presumably we know what Z is, right? So we did all that algebra. Okay, so I claim that Y is P times that. Now why? Specifically, what is it about P that makes this P? Well, it's because I set Z equal to P inverse Y. And why did I set Z equal to P inverse Y? Well, because of how this algebra worked out, I took this P and I moved it over there. It becomes a P inverse, right? And why was this way? Well, because that is that way, right? Because A is PJP inverse, right? Okay, so you can trace it back to the specific, attempted diagonalization of the matrix. And so how this is written, and, by the way, we usually write it like this. Then P is the change of basis matrix, whose columns are the new basis, right? So anyway, ultimately that choice is what causes that conclusion. Yeah. And if it's written the other way, if for some perverse reason A is written as Q inverse JQ, right? It would be super weird. But if it's written like that, and by the way, the world is weird, right? So these kinds of things are perfectly plausible. If it is Q inverse JQ, then this would be a Q inverse right here. And the way you see that is by this decoupling algebra, and that tells you, what to do with at the last step there. Yeah. Right. Okay, so we need to multiply by P. Here's the results of the algebra on the previous page. We found Z3. From that we found Z2. From that we found Z1. Right? Altogether, this is our Z vector. You can write then the corresponding fundamental set of solutions by breaking up this general solution into a linear combination of, don't forget that half there, into a linear combination of individual solutions, so we get our fundamental set. Everybody see what I did there? It's the same move that we did last time, related context. So that's our fundamental set of solutions for the Z's. Keep in mind what we do with the Z's is the Z's go in here, you multiply by P, out comes the corresponding Y's, and that's just matrix vector multiplication multiplied by that P matrix on the previous page, or 2 pages back, and here's your fundamental set of solutions for Y. Okay, so it's a long, slow, annoying process doing the attempted diagonalization followed by back solving followed by convert back change of basis. Kind of annoying, but it works. Okay. All right. What if you're not given the Jordan basis? Let's go back to the original statement of this question. Notice that we were given not only the A matrix, not only the Jordan form, we were actually given the entire Jordanization of that matrix, including the P matrix that does it. As I've mentioned before, finding the P matrix, right, analytically from first principles, it's hard. It's not something we can realistically do in general in this course. So if it's given to you, yeah, sure, you proceed with this tedious algebra. If it's not given to you, what do you do? And there's a couple answers to that question. One is, in the real world, use Matlab. Boom. This jumps all over it. So there's the syntax and everything. This will tell you not only what the Jordan form is, this will tell you what the P matrix is that executes that Jordanization, and off you go. So that's nice. Yeah? Everybody good? So there's a couple other things you can do, and I want to go through and talk about some of these with you. First of all, if you, for whatever reason, don't have access to Matlab, or if just don't want to use Matlab for whatever reason, if you have a 2x2 matrix, it turns out there's some really lucky little coincidences that make it work out just fine and dandy in the 2x2 case. So I want to show you how that one works. There is a homework question that relates to this, by the way. So here's the first little bit of good news. There's only one possible Jordan structure for 2x2 non-diagonalizable matrices. right? I mean, it's only 2 by 2. You could either have a couple of 1 by 1 Jordan blocks. Oh wait, that's diagonalizable. Or it's a single 2 by 2 Jordan block, which has to look like this. So this is exactly the case that we're considering. And what that means is that there is some basis here by which that's the change of basis. Now the bad news, of course, is that we know. Now keep in mind, that we have this first column corresponding to the first basis vector tells us the only eigenvector. So we know how to find eigenvectors. Right? We have this whole process for finding eigenvectors. So V1 you can find. Section 5.4, right? A bunch of details there. Make sure to remember how to do that. But we don't know how to find V2. So finding the Jordan basis, the second vector in the Jordan basis, there's some tricks and it can be done, but we're not going to talk about it in Math 216. Here's the good news. Second bit of good news in this 2 by 2 case. It turns out it doesn't matter what you pick for your second basis vector. Pick any other vector. And let's just see what happens. Now, a side note, not parallel to V1. It's got to be a basis, right? So it's got to be something that's not a multiple of V1. Can't be 0, right? But other than the silly, non-basis options, any second vector that you pick that isn't ridiculous, it's going to turn out to work just fine. And I'll walk you through the process there. So keep in mind what this first column tells us. That's telling us about the first vector and its image with respect to V1 and V2. And that first column then tells us, in effect, this. Right? AV1 is lambda V1. That ends up being about half of what we need to know. Let me give myself some more space to work here. The other half of what we need to know, keep in mind, we have this new basis now. We want to understand what happens to those vectors with respect to that basis. The first equation that we need is this one, thus giving us that first column. Right? Or we're halfway there. The first script W basis vector is V1. AV1 is lambda V1, which is this linear combination of V1 and W. So we're like I say, halfway done. To find the other column, all we have to do is figure out what is AW, and I can take that and plug it in here and work out from, I already know from these two columns, I already know those two equations. Multiply out what happens using linearity for W, and W has as its image, with respect to that basis, BV1 plus lambda W. So this second column. And the great news is, look what's happened. Even though, now, bad news, I didn't get Jordan form, right? We were kind of hoping for Jordan form. This is not necessarily Jordan, but this is probably not Jordan form because that B, I don't know what it is, probably not 1. But who cares about Jordan form? Why did we ever care about Jordan form in the first place? The only reason we ever cared about Jordan form back here in the first place was because Jordan form is back solvable. It's back solvable because this was a natural growth equation. In other words, because of the fact that there are zeros there and there, thus giving me zeros there and there. That's all that we really needed. And notice that's already happened here. Right? That second row, the last equation then, is solvable. So yeah, sure, it's not Jordan form, but who needs it? This is still totally back solvable, just like a couple pages back. And so, for example, let's look at this example. Suppose you want to do this. The matrix is not diagonalizable. Disappointing. you can do some algebra and confirm that that's an eigenvector, 1, 1. And for whatever reason, it doesn't matter, I'm going to pair up that eigenvector with just any old vector. It doesn't matter. I'm going to pick negative 1, 1. I suppose if I'd been a little bit lazier, maybe I should have picked 0, 1 or something. I don't know. It doesn't matter. Right? So let's pick negative 1, 1 because that's already here. This basis, one of the vectors of which is an eigenvector. Do the conjugation. And notice that the result, it's not Jordan form, right? We've got this annoying little 2 right here. That makes it not Jordan form, but it's still back solvable, right? This system right here, you write it out. This system is Z1 prime equals 5Z1 plus 2Z2. And Z2 prime is 5Z2, right? And so natural growth, solve for it. Once you know Z2, you have a non-homogeneous equation you can solve for Z1, and you're done. Well, you're mostly done. Once you have the Z's, then you can solve for the Y's by multiplication. All the usual, change of basis stuff at the end. Okay. All right, so I think that's a neat trick. Heads up for that. Again, there is a homework question where you have a matrix given that's something like this. It's 2 by 2, non-diagonalizable. And the trick I want to encourage you to use is, use this system. Use the eigenvector, then pick any other vector, and use that for your change of basis. Yep?
Can you explain again why you chose WTG minus 1 y?
Yeah, no reason. I don't know. I think at the time I was amused at the fact that it would make an orthogonal basis, but it doesn't matter. So here'd be a great exercise. Pick 0, 1 instead of negative 1, 1. And just, go through the same process and see what happens. Off the top of my head, I don't know. But it does not matter. I could have picked 7, 15 if I felt like it, yeah. I mean, all else being equal, I think I generally tend to encourage more convenient numbers, but anything works. Yeah. Yeah.
Would an orthogonal basis come in handy if we tried to do something else later?
Oh, maybe. Not anything relevant to this question. Yeah. In this question, it really doesn't matter. Yeah. Right. Okay. All right, so here's another alternative method that you can use. Now, this one does require that we know the Jordan form, but it does not require that we know the Jordan. Let's see. Oh, wait, does it? Excuse me. This method requires that we know both the Jordan form and the Jordan basis. So think of this as an alternative to back solving. Right? You still do need to have the Jordan form, and you still do need to know the Jordan basis. So we'd make this very weird definition, and this seems ridiculous. All right, but here we go. We're going to define here what it means going forward to raise e to the power of a matrix. Right? And now, we need to dwell for a moment on what a preposterous suggestion that is. Right? Because you can't do that is right on the tip of our tongues, right? And it's just like, you remember we were talking about in section 5.2 and we were talking about, can you put a differential operator into a polynomial? No, you're not supposed to. Oh wait, no, I guess technically you can. Right? All you have to do is look at what the reasonable definition would be and ask yourself, can you do those things? So that's what we're going to do here. I'm going to define the matrix exponential, e to the power of a matrix. Keep in mind that the exponential is defined by this, is equivalently defined by a Taylor series. And so to be able to raise e to the power of a matrix, all I've got to be able to do is multiply the matrix by itself, a finite number of times, successively. Multiply and divide by scalars. Do that. Add these resulting matrices. All of this is stuff that we can do. And so it's fine. Now, it's a new definition, right? This is a brand new thing. It's kind of a choice, right? But it's not an insane choice. So we're going to define e to the power of matrix like this. And side note, this is what we did with complex numbers, right? A similar complaint could be made. What do you mean raise e to the power of an imaginary number? That's just silly. Well, but this makes sense, right? This is something you can do. You can make this as a definition, and great things follow. So great things are going to follow from this choice as well. A couple of observations. Now, by the way, this stuff I'm talking about here is not in the book. So this is all supplemental, but I like this a lot, and I think you will too, because it's a huge time saver, right? We're all on board with time saving, right? Effort saving. I think you're going to like this. Okay, so here's the big idea. We're going to look at this function, e to the power of, here, give me a second here, e to the power of a certain matrix. The matrix is x times a. All right, this is just a choice. I want to look at the matrix being x times a, not a itself, but x times a, where x is my variable. A is my constant matrix from the differential equation. And it turns out that the derivative of this, if you go through, plug into the definition, take derivatives, rewrite, the derivative of e to the xa is a times e to the xa. It's just like it was in single variable calculus. Right? Isn't that weird? It's just the same thing. So let me say that a little bit differently then. This function, e to the xa, has the very familiar feature that taking a derivative of it is the same as multiplying it by the matrix A. And amazingly, that instantly makes it a solution to this differential equation. Check this out. Look at that. Y prime equals AY. This function when you take the derivative of it, you get A times itself. So this one calculation up here of playing around with the power series a little bit shows that we have solutions to this differential equation. Everybody on board? By the way, wasn't that easy? Right? Now, bad news. The bad news is this makes it look like whenever we want to use this trick to find solutions that I'm going to have to write down an infinite series of matrices. And that seems difficult, right? I mean, every time I want to evaluate a solution, you're telling me I've got to do all of this nonsense? And no, it turns out that there's a better solution than that. By the way, quick observation, you can multiply this solution times any constant, color coding, times any constant, such as a constant vector like that. This still a solution. You just multiply by a constant, it's still going to work. The derivatives work the same way. So these are solutions to these initial value problems. Okay. All right. So how do you evaluate these things? We don't have time to go through the details. And again, this is all supplemental, so I feel very comfortable with kind of sweeping a bunch of details under the rug. But this is a rewrite of the definition of a matrix exponential, rewritten in a certain way that allows for seeing how this exponential factor shows up. And some consequences of this are as follows. First of all, if you want to multiply a matrix exponential times an eigenvector, easy formula. Matrix exponentials times eigenvectors are easy. So that's a good thing. Some more details I'm going to have to sweep under the rug. Again, time being a factor. And all of this makes perfect sense. It's just a matter of details. You'll even recognize some of this. Remember how columns give you equations? We talked about this long ago, right? Back in chapter 5. And you get certain nice conclusions about what A minus lambda I does to Jordan basis vectors. It's perfectly readable. You're welcome to take a look at it if you like. You're not responsible for it. Don't worry about it if you're not curious. But you get this lovely punchline here. And that is that if you want to multiply a matrix exponential times a Jordan basis vector, formula. Okay, so I'm going to show you how to use this formula now. Let's look at this case here. Now, this is the exact case that we used, the first example that we did here in section 6.3. And remember what we did previously was we took the Jordan form and we went off and made a not decoupled system, and we did that whole back solving thing, and yikes, right? The back solving was a lot of work, right? A lot of effort there. Okay, so here's what we're going to do instead. We're going to use this equation that, that gives us solutions. The process goes as follows, and again, I've skipped a bunch of details that you don't need to know about the why. You just need to know the what. And the process is take the Jordan basis. There's the Jordan basis. That Jordan basis, use those Jordan basis vectors as what you multiply by the magic matrix exponential function, e to the xa. So you complain, okay, yeah, but I don't know what this matrix is. I don't know how to write this matrix. Keep in mind, we don't need to know how to write the matrix. I just need to know how to multiply it by these Jordan basis vectors. How do you multiply e to the xa times a Jordan basis vector? We use this formula. That comes from there. Let's take a careful look at this formula. Notice that this formula says that you start with whichever Jordan basis vector you're looking at. If you're looking at the ith Jordan basis vector, you start with wi, and then you just keep going through this equation where in each term you get the previous Jordan basis vector. That's just how this works out. So that's a wi minus 1, wi minus 2, and you just keep going back until you run out. That's the formula. So starting with the first Jordan basis vector, this being a 1, that being a 1, that's a 1. That is the first Jordan basis vector. There are no previous Jordan basis vectors, so all of these terms go away, and this becomes that. All right. Next. Now let's look at the second one. Let's look at W2. That means this is a 2. That means this is a 2. That means this is a 1. And that's the first Jordan basis vector we've run out, so there's no extra terms over here. And this becomes that. Oh, sorry, I missed. Sorry. Becomes that. There's our second basis vector, etc. Right. So this is just a direct sort of, plug in one at a time sort of a system. Last example, looking at W3. That's a 3, that's a 3, that's a 2, whoops, that's a 1. Now we've run out. There are no extra terms over here. That becomes that. Okay, you'll even notice kind of a pattern here. It's like this looks an awful lot like, well, I mean, it is just one vector, right? This kind of looks like a sort of a first order Taylor polynomial. This kind of sort of looks like a kind of a second order Taylor polynomial. And structurally, it's not that far off, right? So it's an easy pattern to notice. And then observe that it's just a matter of plugging in at this point just a matter of plugging in. Keep in mind, we know what W1, W2, and W3 are. Those are these Jordan basis vectors. So W1 goes there, there, and there. W2, let's see here, I'm kind of running out of colors. W2 goes there and there, and W3 goes there. And that gives us the exact same solution that we found after tedious effort in back solving the way we did it at the start of class. So you have a choice, right? So if you find yourself looking at a non-diagonalizable system, you can do the whole back solving thing, right? There's a lot of little details. And by the way, where there are details, there are opportunities for oopses, right? So it's a long, treacherous road to go down doing the back solving thing. The alternative is to use this trick with matrix exponentials. There's a couple of things to keep track of. You've got to remember this big formula up here, or at least you've got to remember the pattern suggested by this big formula here. But at that point, it's mostly a matter of just writing the answer down. So, take your pick. It's up to you. Okay, y'all have a great weekend. See you later.